Hello everyone, thank you for joining my talk. This is Leng. I'm an assistant professor at UT Austin. Today I'm presenting a work joint with my colleague Ashish, who is in the audience, and our PhD student Yunxin Sun on a new method to reduce preference disparities between LLM and human samples for sample collection. We all know that LLM excels at understanding and mimicking human-generated content. Thanks to the large corpus that they are trained on, LLM offers a powerful tool to synthesize and aggregating human opinions and preferences. This provides great opportunities for researchers to explore LLM's potential in sample collection applications by simulating human responses. Comparing with traditional data collection method, LLM offer the potential to improve the speed and reach of the sample collection, but also at a much lower cost. There is a growing number of recent social science applications, such as in using LLM to monitor consumer preferences in marketing applications, or for monitoring public sentiment for societal issues. However, despite that LLM have access to a large training corpus, whether these corpus can represent the population of interest, even it is, whether LLM can accurately infer human preferences from this large corpus is largely questionable. And from users' perspective, LLM remain largely enigmatic and opaque, meaning that we couldn't really understand what's happening behind the scene. There is also a growing number of evaluation papers that try to say that LLM actually struggle to fully represent human. One of the most obvious applications seems to be use LLM in monitoring public opinion on societal issues because of the large training corpus available online. However, many papers started to show that LLM actually provide very biased responses in comparing with humans. In order for LLM to represent economic behaviors of humans, this needs to have human-like economic preferences or human-like mental, behavioral or cognitive biases, which are only partially present in LLMs. Despite the recent literature in marketing in showing LLM's application in estimating price elasticity or perceptual map, there is still a large room for improvement. So that leads to our research question, which is to improve the accuracy of LLM samples in representing human preferences and opinions. Now let me talk about our research framework. For a particular application or sample collection task of interest to researchers or practitioners, we need to collect LLM responses from different demographics groups. In the same time, we need to collect human preferences and behavioral data that match with the same application. And this human data is used for two purposes. Partly it's used to better align LLM with human responses, and partly it is used to do evaluation. And our goal is to learn an optimal ensemble of LLM, which involves learning the sample weight for each demographics group of LLMs so that they can better reflect human responses. At the same time, we want the model to have good properties. First, we want it to be model agnostic, meaning that it should work regardless of the model being open weight, like Llama, or its proprietary, such as Gemini or GPT. And it should be able to work on top of different model iterations. And second, it should be scalable, meaning that it should be accessible to social scientists and the practitioners who don't have a lot of computational resources. And the second question we ask is, to what extent can the LLM sample weights be transferred across different domains? This is mostly because human data collection is costly and time-consuming, and if we can collect human data on LLM data on a small sample, then we might be able to use it in broader applications, such as to apply it to another spatial region, to a different industry, or different survey topics. So in terms of a method, we have an optimization method that we want to calibrate LLM output to closely match human data for any given applications of interest. And basically, we want to minimize the distance between LLM and human responses for a set of questions. And the solution to our optimization is to learn a weights for each LLM demographics group so that we can minimize the distance between the two. And because we work on top of the output directly provided by LLM, and you notice that our model has the good property that we want, it is scalable and it's also model agnostic. And in this optimization problem, the most important thing is that one needs to decide what is the distance function that one should use to minimize the difference between LLM and human responses. And we determine the distance function based on the type of data that is collected on LLM and human. The first type of distance function is this Versus-Stein distance, which can be used for continuous or categorical data. So for continuous data, there has been some marketing papers that used to collect humans' willingness to pay, their likelihood of purchase, or response to different interventions. And for these type of applications, continuous data is being collected. For example, we might ask if LLM is a consumer in a store and see some information about Coca-Cola, how likely it is to purchase a product. And the second type of data is this categorical data that is in discrete groups or categories that can be used for multiple choices or yes or no questions. And LLM has been used to collect public opinions or consumer surveys with discrete choices on these type of questions. And for example, this is a question that we can ask LLM to monitor LLM's opinion on how healthcare would contribute to the overall economy. And we use Versus-Stein distance to calculate the distance between if the data is in continuous or categorical form. So basically, Versus-Stein distance can help us to calculate the cost of transferring the LLM distribution to human distribution. And for continuous data, we basically take the infimum over all possible transformations. And for a categorical data, we take the absolute differences between the cumulative distribution functions. And the second type of data you can collect will be in ordinal form. Basically, we might be interested in asking LLM to provide a ranked list. And for this type of data, the distance between the categories are not naturally defined. And in terms of practical application, we can use it to collect LLM's responses for, let's say, if we ask LLM for what are the brands that are associated with a given brand, and LLM can provide a list of similar business in ranking order, or it can be used to collect information about policy ranking or candidate ranking in voting. And to calculate the distances between these ordinal data samples, we need to use Kendall-Style distance, which basically calculates the percentage of matched pairs between LLM responses and human responses. So that wraps up our framework, and we apply our method to two types of application. One is preference learning, and the other is opinion learning. So we start with this type of revealed preference learning, and the specific application is to use it to understand the market structures, which can help brands identify associate brand with the brands that they work for, so that this can improve their operation and marketing strategies. In terms of the data, we estimate the local market structure for department stores in Texas, and we do so for the top 12 department stores according to the revenue. For LLM responses, we collect it from GPT-4, and we collect LLM responses for 90 demographics group with a combination of income, gender, and age. For example, we ask LLM to imagine itself being a certain demographics group who has made a purchase at the focal brand, say TJ Maxx, and we ask which are the 10 brands this person will likely to visit in ranking order. And in terms of human data, we collect bank transaction data from Yardley, which is a financial intelligence firm. This bank provided transaction data collected from 16 out of the 20 largest US banks. And to process this human data to be comparable to our LLM responses, we construct the co-transactions among customers. So basically, if customer visits one store, which are the other stores is likely to visit, and we aggregate so for all of the population. And we first look at our performance improvement comparing with two benchmarks. The first one that is used in the literature will be uniform aggregation, basically without any persona, but we would uniformly aggregate across all of the LLM queries. And the second one is population density-based weighting, that we weight the averages of each demographics group according to the population density, and the density data is collected from American Community Survey. And in terms of a performance metric, we calculate the concordant pairs between LLM responses and human responses. And in terms of our improvement over the two benchmarks, we notice that we can improve over 30% comparing with uniform aggregation and about 22% over population-based weighting. And then we want to ask whether the calibrated weight learned in one spatial region can be used in other spatial regions. So if this works, then we can collect data only on one area and use it in others. This can be particularly useful when data is scarce or expensive to collect. And practically, we migrate the weights from the state of Texas state to 3 other most popular states in US, New York State, California, and Florida. Because the population density between these states are different, meaning that the population contribution to the training corpus can be different across these states as well. So we adjust weights that we learned in Texas state to the new state according to the population density ratio between the new and the original region. And overall, we noticed that our method can consistently improve the concordancy between LLM and human across the 3 states, with the most prominent improvement in California. And by comparing the results of uniform and population weighting, we also noticed that population weighting doesn't consistently perform well. For example, it would perform not as well in Florida. And the next task is more challenging. So we want to ask whether the weights learned in one sector, in our case it's department store, can be used in other sectors. So here we migrate the weight to clothing and restaurant. And by looking at the results, we see that we can perform better than uniform aggregation, but we actually perform slightly lower than population density weighting. Now, this tell practitioner and researchers when use this type of method is that if they want to utilize it in another sector or industry, then they would be better off just do another set of calibration on the new sector. The reason being that the population composition to the training corpus of LLM can differs when the corpus changes, as also human consumer profiles and preferences can change across different sectors as well. In our second application, we use our method in opinion learning, which basically can be used to use LLM to monitor public opinion about different societal issues. And here, we collect human data from American Trends Panel by Pew Research, and including 372 opinion questions that cover this list of topics on research, economy, gun, race, and gender. And the LLM data were published by a research group in Stanford, where they published the LLM responses for 10 different language models. And by applying our method to this application also shows our flexibility in terms of combining the responses from a combination of LLM models. For robustness, we calibrate separately for 4 demographics groups. This would include political party, political ideology, race, and religion. The first question we ask is, can calibration improve the alignment of LLM output with public opinion? So here you see 4 figures. The 4 figures correspond to the 4 demographics groups that we calibrate. And the clusters on the axis correspond to different research questions. And the y-axis show the reduction in versus time distance comparing with our method over the benchmarks. And we see that our method can consistently improve across the 5 domains and 4 social demographics groups. And we also see larger improvement for gender, race, and gun. And here we notice that in this application, population weighting perform comparably to uniform weighting, and in some cases, it even performed worse. This is likely due to the misalignment between LLM opinions with these human responses. And our last result, we want to ask, can the model weights calibrated in one topic to be applied in other topics? So here on the heat map, we show the performance of transferring from a region on topic, which is shown on the y-axis, to the target topic, which is shown on the x-axis. And blue, darker color means better improvement. So here we see that within cluster, meaning that if we want to migrate the weight from some questions that are seen to some unseen question within the same cluster, the performance is consistently very strong. And for cross-cluster migration, we notice that the performance is generally effective, and is especially so when we are calibrating for political party and political ideology on the upper panel. And we also notice strong transfers from economy to all other factors, and a weaker transfer from gun to race or political to race. we try to investigate a little bit to understand why there is a stronger, some are stronger and some are weaker. So we project the sentence of the research of the question that are being asked to to some embedding spaces, and we notice that the closer the cluster semantic proximity, the better the transferability. And to conclude, we propose a new scalable and model-agnostic approach to reduce the disparity between LLM output and human output. This adds to the growing body of literature of LLM in using LLM to represent human data to learn human preferences. And this also provides a new sample aggregation method to the sample design literature. We show that conventional population weighting may not be effective for LLM, mostly because they can provide biased group level estimates. We demonstrate the effectiveness of our method in 2 applications, preference and opinion learning, and we also show some transferability results for cross-spatial region and cross-topics. Of course, this whole field is still evolving, and I think there's some distance before we can actually use this in practice. And I think more empirical analysis, benchmark data set, and evaluation frameworks are needed to evaluate these models as new LLM models are launched onto the market. And there are studies that are needed to evaluate their performance as well as their boundary condition for the transferability. Unfortunately, our method is agnostic to the model, so that can be used when new model is launched. With that, thank you for your attention, and I'll take questions. Wait.
For the method part.
Can you hold on 1 second? Sorry, we are recording, so we want to just catch this.
Very interesting work. So I have 2 questions. First, for the method part, what's the difference from like reinforcement learning with human feedback and direct optimization of human preference, this type of methods? Second, the second question, the task that you are working on seems to be a transfer learning task. And how much is the result affected by the out of distribution of the data? I think yeah.
Yeah, let me answer it one by one. So first, so like in LLM, there are some more complicated methods like human feedback reinforcement learning, and those data directly optimize on top of the parameters of the model, meaning that they are not really scalable, and it's very hard for social scientists to use because you need really strong computational resources to use the stronger models. So basically, and another benefit of our model is that you don't need a lot of data. But if you're using those complicated reinforcement learning methods, you need to collect a large amount of data because there are billions of parameters that you need to optimize. So our method work on top of the output already produced by LLM responses. So the benefit is that it's more scalable, and also it requires a very small sample. And so in terms of out of distribution, so I think that goes back to the boundary condition of the transferability. I don't have good answers for that because that would be a domain-specific question. I think definitely more studies would be required to evaluate the transferability across conditions. So our method can work. Our method would work for the conditions where the distribution should be similar. So it's not supposed to work on out of distribution cases. And I think more studies should show. Should look into which of the applications has similar distributions so that this type of method can be used. Thank you.
We have time for one more question.
So thank you. So what is, I guess, the difference? Have you looked at the difference between the weights, the rescaling between different large language models? Like as you tested with many different models, like do they vary largely in terms of the calibration effect that you need?
Yeah, so actually in our second application, what we do is that we combine different models instead of calibrate separately for each of them. So it's not a direct comparison across models, but my intuition is that if you certainly can calibrate for each single language model, my intuition is that they will vary significantly, just because my experience with working with different language models is that they can produce very different responses, especially if the company are built by different, if the model are built by different companies because, for example, they have different alignment process, company have different values that would affect the parameter. So yeah, my intuition is that the weights could be quite different if you use a different model.
All right, thank you so much.
Thank you.